Welcome back. So, this is lecture 14th in this course. My name is Himanshu, and we were talking about likelihood function in the previous lecture. The topic of this lecture is conditional probability. So, we will step by step understand conditional probability, independent events, law of total probability, which will lead us to the main concept of interest, which is Bayes theorem, which would be instrumental in this course, right? So, let us start with conditional probability, right. So, suppose I ask you that what is, let us say you have two events A and B, and these events exist in your event space F, right. If I ask you what is the probability of occurrence of event A given that event B has already occurred. Okay. So, what is the probability of occurrence of event A given that event B has already occurred? Okay. And this kind of question you can always ask in the situation when events A and B are not exactly independent, right? And I'll come to that independence point later. But this is the question you can always ask, that what is the probability of event A given that event B has already occurred. So, there was some event B which has already occurred in the past, and it would have some effect on this new event, event A. Okay. And we are asking what is the probability of occurrence of event A given that B has already occurred. Okay. So, there is a formula for this. This thing is called conditional probability of A given B. Okay. So, probability of occurrence of event A given that event B has already occurred. This is called conditional probability of A. Conditional probability of A given B. Okay. And there is a formula for conditional probability. Formula is this, that probability of A intersection B divided by probability of B. What is A intersection B? Probability of joint occurrence of these two events A and B divided by probability of occurrence of event B. There is also condition that probability of B should not be equal to 0. Okay, in that case you won't be able to calculate this conditional probability. Okay, so this is the formula for conditional probability. Okay, so let us see what does this mean, and let us try to verify this formula. Let us take an example. Let us take an example where you are tossing 3 coins simultaneously. Okay, so it's a 3 coin toss experiment. In this experiment, you're tossing 3 coins simultaneously, right? What could be your sample space? Sample space would be this. It would have 8 possible outcomes. There are 8 possible outcomes when you toss 3 coins simultaneously. Whether you obtain heads on all 3 coins, whether you obtain head, tail, heads, or head, head, tails, or head, tail, tails, or tail, head, head, tail, head, tails, tail, tail, heads, or tail, tail, tails, right. So, there are 8 possible outcomes. We are tossing 3 coins simultaneously. Okay. Now, let us, and if you want to construct event space would be huge, right. All these 8 outcomes would become elementary events, and there would be much more combinations of all these, right. So, all possible subsets will be huge, right. So, let us talk about these particular events in the event space. Let us say E1, or maybe let me just call it A. Let us say event A. Event A is this, that we obtain at least, or let us say we obtain exactly 2 heads. That is event A. Okay, it's an event of obtaining exactly 2 heads, right. So, in what situation you would obtain exactly 2 heads? in which outcomes you would obtain exactly 2 heads. This is one possible outcome, this is the possible outcome, this is the possible outcome. Okay, that's it. So, in these 3 outcomes you would obtain exactly 2 heads. You can write them like this: HTH, HHT, THH. Okay, and let us say event B is the event where you obtain at least 1 heads. Okay, or maybe just two, let us say at least 2 heads. Okay, to make it comparable. So, event A is event of obtaining exactly 2 heads, event B is an event of obtaining at least 2 heads. Okay. So, that means all the possible outcomes which contains 2 heads as well as outcomes which contains 3 heads, right. So, basically it would add one more outcome to the list: HTH, HHT, THH and HHH. Okay. So, this is event A, this is event B. Okay. Now, let us say you are interested in calculating conditional probability of A given B. What is the conditional probability of event A given event B? So, what is the probability of occurrence of event A given that event B has already occurred? Okay. So, do you remember the formula? So, this is probability of A intersection B divided by probability of B. Okay. That means it would be probability. What is probability of A intersection B? So, if you see A intersection B, A is this, right? B is this and this, right. So, if you calculate A intersection B, it would come out to be actually just probability of A, right. Basically just probability of these this thing, right. This is the common element between A and B. And if you divide it by probability of B, then you will get probability of A given B. Okay. Now, in order to calculate this, you will need to know what is probability of A, what is probability of B. How do we calculate that? Well, you can only calculate it only if you know some assumptions about this coin toss experiment. So, let us say you are given that each coin toss is independent of each other and the underlying probability of obtaining heads is 0.5. So, probability of obtaining heads in a particular coin toss is 0.5 and these coin tosses are independent. So, that means you can calculate probability of obtaining HHH, which would be 1 by 2 into 1 by 2 into 1 by 2. Okay. So, you can use this thing, right. So, what it would mean, by the way, there is another way in which you can do this, which is that you apply 3 axioms in such a way that let us say you are just given that each outcome is let us say equally likely. Okay. So, that would happen if the coin is fair. Okay. So, let us say each outcome is equally likely, right. So, let us do it that way. So, let us say you are given that each outcome is equally likely in your sample space, right. Okay. So, if you apply the second axiom and the third axiom, right, then you would have this, that probability of HHH, this is usually the result that we get from second axiom and third axiom, that summation of probabilities of elementary events is equal to 1. Probability of HHT and so on, probability of T to TTT. So, probability of all these 8 elementary events is equal to 1. And if you are given that each of them are equally likely, then probability of each of these possible outcome is 1 by 8. Okay. So, probability of each elementary event is equal to 1 by 8, right. Now, you can easily calculate probability of A and probability of B. What would be probability of A? So, probability of A will be probability of HTH plus probability of HHT plus probability of THH, right. Probability of HHT plus probability of HTH plus probability of THH. So, that would be 1 by 8 plus 1 by 8 plus 1 by 8. This would be 3 by 8. Similarly, probability of B will be 1 by 8 plus, because B has 4 elementary events, 1 by 8, 1 by 8 plus 1 by 8, it would be 4 by 8. Okay. So, what would be conditional probability of A given B? So, this would be 3 by 8, which is basically probability of A divided by probability of B, 4 by 8. It comes out to be 3 by 4. So, that is the conditional probability of A given B. Okay. So, we have calculated this using this formula. Okay. However, you can calculate the same thing using just a conceptual idea, and let me show you how. So, what is conditional probability of A given B conceptually? This is the probability of occurrence of event A given that event B has already occurred. Okay. What this actually means is this, that if you think that B is your sample space, okay, if you think of B as your sample space, okay, and then you apply 3 axioms accordingly, then whatever probability of A you will get will be your conditional probability of A given B, right. Then you do not need to apply this formula at all, you just assume that B is your sample space and then calculate the probability of A. So, what I am saying is that you calculate probability of occurrence of event A given that B is your sample space. It means actually the same thing as saying that what is the conditional probability of A given B. Let us see how. So, let us think of B as your sample space. What is B? B are these events, at least 2 heads occur, right. So, B is HTH, HHT, THH and HHH. So, let us say this is your new sample space. Okay. So, if this is your sample space, then if you apply the second axiom, then it would say that probability of B is equals to 1. That is what the second axiom says, right. More precisely, probability of HTH union HHT union THH union HHH is equal to 1. And third axiom says that probability of union of all these elementary events, which are of course mutually exclusive, then their probabilities would be equal to probability of HTH plus probability of HHT plus probability of THH plus probability of HHH will be equal to 1. So, this comes from second axiom. So, from second and third axiom you have this result, okay, and this is precisely because we assumed B is your sample space. So, you get this result, okay. And now you are given that each event, each elementary event is equally likely. So, each outcome is equally likely, right. So, because of that all these probabilities will be equal. So, that means probability of HTH and also all these probabilities HHT, okay, equals to THH equals to HHH would be equal to 1 by 4. Okay. If they are equally likely, their probabilities, individual probabilities are equal to 1 by 4. Okay. So, this is the result you have driven, okay, assuming B is your sample space. Now, that is it. Now, you only need to calculate probability of A. So, what is A? Event A is actually HHT. So, event containing exactly 2 heads, HTH and THH. Okay. So, that means probability of A will be probability of HHT plus probability of HTH plus probability of THH. Okay. What is probability of HHT? You can see it from here, 1 by 4. Assuming B was your sample space, this would be the probability of HHT. Probability of HTH is 1 by 4, probability of THH is 1 by 4. So, the probability of A that you obtain now is 3 by 4. This is exactly the same as conditional probability of A given B, right. So, this one we calculated using formula, this one we calculated conceptually, assuming B is your sample space, what will be the probability of A, okay. So, that is the conceptual idea of conditional probability. So, the conditional probability of an event A given B is the probability of that event A, assuming that B is your sample space, right. So, what is the probability that A occurs in this sample space B, right. And the formula you have also seen, it is probability of A intersection B divided by probability of B. Okay. So, this is conditional probability. Now, from conditional probability, we can easily think of another very interesting concept, which is independence of two events. Okay. When do we say that two events are independent of each other? So, let us say you have two events A and B, okay, which belongs to your event space F, right. In what situation you can say events A and B are independent? What is independence of event actually means, right? Independence means is that the occurrence of event B does not affect event A, right? So, occurrence of B does not affect occurrence of A. Okay. So, let us say probability of event B does not affect what would be the probability of event A. Just that. So, they are independent in the sense that occurrence of one does not affect the occurrence of the other. By the way, in what situation you can think these events may be independent, not independent? So, let us think about it like this. So, let us say you are tossing the same coin multiple times. Okay. Now, in this case, whatever you obtain on the first coin toss would not affect what you would obtain in the second coin toss, right? So, let us say in the first coin toss you obtain heads, that would not affect what you would obtain in the second coin toss. Second coin toss you can still get a heads or tails, right. But let us say you are in a situation where you are doing a word recognition task, where the participant has to recognize whether a string shown on the screen is a meaningful word or not. So, let us say they need to decide whatever they see on screen, let us say BKTR, and they need to respond whether it is a meaningful word of English or not. So, they respond with keys, right. Now, in this case, in the beginning you can think that, well, in the first trial they responded with yes and no, and whatever, whether it was correct or incorrect. In the second trial they will again respond with yes and no, and maybe first and trial and the second trial are independent of each other. Okay, that's likely. But as you go on through the experiment, let's say you do 50 trials, okay, then what might happen is that there is a practice effect, that these participants get better at doing this task. Okay, so they get more accurate, they get more better at doing this task, and eventually what would that mean is that as they go on later in the experiment, let's say towards trials between 40 and 50, they would have higher accuracy. So, in that case you cannot say exactly that these trials are independent of each other. Okay. Similarly, let us say if there is fatigue effect. So, let us say these participants are getting tired after certain amount of trials, right, and that fatigue would increase trial by trial. So, later on in the later half of the experiment, participants are completely tired, and the tiredness will keep on increasing trial by trial, right. Now, in this case their performance is decreasing. So, you cannot exactly assume they are exactly independent, right, these trials are independent. Okay. So, there are situations we will come across these later on, where you can assume that certain events are independent or not, right. But here we are understanding it conceptually. So, two events A and B are independent if occurrence of event B does not affect occurrence of event A, and vice versa, that occurrence of A does not affect occurrence of B. Okay. Now, a way to represent this statement mathematically is this, that probability of A given B gives us the conditional probability of occurrence of A given that event B has occurred. Okay. Suppose probability of A given B is equals to probability of A. What does this statement mean? That probability of A given B is equals to probability of A. This statement means is that probability of occurrence of event A does not depend on B at all, or is not affected by B at all. So, when you are calculating conditional probability of A given B, it is same as probability of A. So, basically it is not affected by B at all. Okay. Conditional probability of A is same as probability of A when there is, let us say, no condition of B, right. So, A is not affected by B at all. Okay. This is exactly the condition of independence of events, right. So, you can say that two events A and B are independent of each other when probability of A given B is equals to probability of A. In fact, it's said in the other way that if you say that two events A and B are independent of each other, that is occurrence of A does not affect occurrence of B, then this statement will hold that probability of A given B is equals to probability of A, right. So, this statement gives you independence of events, right. But you have learned the formula of probability of A given B. What was the formula for probability of A given B? A intersection B divided by probability of B. This was formula of A given B. When events A and B are independent, when A and B are independent, then this thing will be equal to probability of A, right. What does this imply is this, that probability of A intersection B will be equal to probability of A into probability of B when two events A and B are independent of each other. And this is exactly the reason why we multiply probabilities in order to calculate joint probability of something. Okay. So, if you want to calculate joint probability of two events, we multiply their individual probabilities. Okay. And we can do this only when we assume that A and B are independent of each other. So, under the assumption of independence, we can say that probability of A intersection B, basically probability of joint occurrence of A and B, is equals to probability of A into probability of B. Okay. So, this is the result we have gotten. So, if two events A and B are independent, then we can say probability of A intersection B equals to probability of A into probability of B. Okay. So, that is the idea of independent events. All right. Now, there is another very interesting and useful concept, which is the law of total probability. Okay. Law of total probability. So, let us say this square rectangle represents your sample space omega. This is rectangle represents your sample space omega. Okay. And there are multiple events, basically subsets of the sample space. We call subsets the events, right. Let us say there are multiple events E1, E2, E3. I have just basically I have segmented this rectangle into multiple rectangles, multiple strips, right. E4, let us say En. These are multiple events, right, but such that the intersection of all these events is an empty set. Okay. So, all these events are mutually exclusive. So, E1 to En are mutually exclusive. So, they do not contain any common element. So, these are mutually exclusive. Also, they are exhaustive. What exhaustive means is this, that if you take union of all these events, E1 union E2 union E3 union En, then this would be your sample space. Okay. So, this is called exhaustive property. So, all these events are exhaustive as well as mutually exclusive. If you take their intersection, then this is an empty set. Okay. So, for events E1 to En which are mutually exclusive and exhaustive, basically I have divided this rectangle into these strips. Okay. If this is the case, right, and let us say you have another event B here, this is event B. Okay. This is event B. let us think about these particular events which are basically intersection of event B and these mutually exclusive and exhaustive events E1 to En. So, B intersection E1, B intersection E2, B intersection E3 and so on. Okay. Let us say I want to calculate probability of B intersection E1 union B intersection E2 union B intersection E3 and so on. Okay. Now, can you apply the third axiom here? You can, because B intersection E1, B intersection E2, B intersection E3, all these events are going to be mutually exclusive. Yeah, you can see here. So, let us say this particular interval and this particular interval, they are mutually exclusive from each other. They do not contain any common element, exactly because E1 and E2 are mutually exclusive. Right. So, these are all mutually exclusive. So, if you apply third axiom, then you can write this as probability of B intersection E1 plus probability of B intersection E2 plus probability of B intersection E3 and so on, right. Let me write it in the short form. So, what we are saying is this, that's probability of union from I equals to 1 to n of all these terms B intersection AI is equals to summation of probabilities of B intersection EI. Okay. So, that is the result, that is the thing that we are talking about, right. Now, what would be this term? So, basically probability of B intersection E1 union B intersection E2 union B intersection E3. Okay. Actually, you can apply one property that we know from union and intersections. If B intersection E1 union B intersection E2, we can rewrite the same term like this, B union E1 intersection E2 intersection E3 and so on. So, I have written the same term like this. Left hand side I will keep it same, basically summation of B intersection EI. On the right hand side you have this. Okay. What would be intersection of E1, E2, E3 and En? Intersection of all these events? Well, all these events are mutually exclusive, right? We have seen this property already. So, their intersection will be an empty set. So, what that leaves us with is B union an empty set, which is basically B, only event B. So, probability of event B is given by summation of probabilities of B intersection EI, right, where EIs are mutually exclusive and exhaustive event. Okay. Right. Now, you can rewrite this term probability of B intersection EI. How? You know something from conditional probability formula, that probability of B given EI is probability of B intersection EI divided by probability of EI. Okay. So, probability of B intersection EI would be probability of B given EI into probability of EI. Okay. So, what that would give you is this, that probability of B can be written as summation across, sorry, I is equal to 1 from 1 to n. So, summation of probability of B given EI into probability of EI. Okay. So, if you have mutually exclusive and exhaustive events E1 to En, okay, and then there is another event B, and if you want to calculate probability of B, then it can be given by probability of B given ei into probability of ei and its summation from 1 to n to all summation across all mutually exclusive and exhaustive events. This is called the law of total probability, and this is called total probability of B, total probability of event B. Okay. If you want to write it in more general form, you can think of you can basically you can call these events E1, E2, En rather than calling them E1, E2, En. You can call them A1, A2, A3, En, right? So I'm just changing the symbol, right? So rather than writing E, I'm writing them as probability of B given AI into probability of AI. Just to basically have just consistency of terms A and B, right? But these are just event, doesn't matter what you call them. You call them E1, E2 or call them A1, A2, that doesn't matter. So this is law of total probability, and this would become very useful when we later on discuss the Bayes theorem. Okay. All right, so I will stop here. In the next lecture, we will talk about Bayes theorem using these concepts of law of total probability and the conditional probability and the independence of events. Okay. All right. Thank you very much.